With that, I'm very proud and excited to introduce Dr. Satoshi Matsuoka. I've known Satoshi for decades, probably. He is globally renowned as a leader in high-performance computing and computational science. He's at RIKEN, one of the world's leading computational research centers, and I could think of no better person to kick off our fall programming with a presentation covering multiple advanced computing technologies and how they will transform science. So please welcome Satoshi Matsuoka with some applause emojis. And Satoshi, you can come on screen and off mute. There you go. Thank
you, Jay.
G.
Well, thank you, Jay. Thank you, everybody. Let's see, more than 100 people attending. I'm quite honored to have such a large audience. It's early morning in the U.S. I'm in Kobe, Japan right now, so it's 1 a.m. My 1 a.m. past midnight. But I'm very happy to be here and be able to present some of the work that we're doing RIKEN at my center, which has several hundred people, and we're doing HPC, AI for science, and more recently hybrid Quantum-HPC. So I'm going to talk about some of those, and also I'd like to talk about some of the future prospects, because we launched several projects, but the most recent one is our next generation supercomputer, in which we hope to achieve, extra leap in both HPC and AI performances, working with the top vendors like NVIDIA and Fujitsu, and also with other parties like some of the DOE labs and our European friends. So I'm going to talk about, but what are our objectives, what are our thoughts with regards to the progress that we can make over the next several years in terms of advances and high-performance computing coupled with AI. Okay, so hopefully I can cover all that within my allotted time, and hopefully I'm successful in sharing my slide, because it's a little complicated. Apparently, it's a little complicated procedure. So we'll click on what. Okay, I will resume my. Okay, so don't worry about this mirror thing. So apparently that's what it's supposed to do, and I'm supposed to put my PowerPoint in presentation mode first, and go to the first slide, and then somehow manage to get back to Google Meet, and then somehow manage to share the entire screen. So I should have AI doing this, but did I have to use human intelligence? Oops. And but then go to PowerPoint slideshow. Okay.
There you go.
Oh, is this working?
Yes.
Good. Technology, human intelligence prevents. Okay. So again, I'm Satoshi. I'm the director of RIKEN Center. It's our center is the national flagship center for high performance computing in Japan, where we host currently we have designed and host a supercomputer like this. It's called Fugaku. Fugaku means Mount Fuji. It's an alternative name from Mount Fuji. So it's a fairly large supercomputer. It's like a small. It's like one of your smaller hyperscaler data centers in terms of number of nodes. So it currently has 160,000 nodes. Each node is a special high performance oriented ARM processor that we designed and built with Fujitsu. And each node has 48 cores, so about 7 million cores in total. And it's a running production machine today. So one may argue that yes, there are similar or even bigger cloud infrastructures, but we must make note that this is a single machine. And also, it's a machine designed to run all 160,000 nodes without failing. So we can run a full capacity job involving 7 million cores for 24 hours. It doesn't fail. So it's sort of a supercomputer designed from ground up instead of batching together a whole bunch of processors off the shelf. So it has lots of special features, but today I won't go into it too much. But it's it's a workhorse machine. It's always full, 95% capacity, and so forth. And we got lots of fantastic scientific results, and also we have up to when we commissioned it in 2020, it was the fastest machine in various benchmarks, including not just top 500 that impact, but some like HPCG. I think Mike Haru was in the audience. That's the benchmark he invented. So we just lost on the Mullen status there, number 2 to El Capitan, but still we're very happy. Graph 500 was still number 1. So it's a machine that's sustained this very high rankings in all the benchmarks for 5 years now. But also, benchmarks are one thing, but we have significant scientific results, multiple the so-called Gordon Bell Awards in COVID mitigation and high resolution forecasts, laser manufacturing, and so forth. So it is a supercomputer that not only has been designed to push the limits of technology in terms of scaling and performance, but also it's a supercomputer that has, as a result, have brought about a significant number of groundbreaking scientific results that have really impacted society, saved lives, and so forth. And as a result, so we worked with Hyperion Research. Hyperion Research is one of the consulting firms in the U.S. That does analysis of HPC. And they work with DOE labs, they work with the Europeans, they work with Google, and so forth. And so they're very trustworthy. And we asked them to commission them to do the analysis of the economic impact of Fugaku, and they came up with a number which is quite astounding. That the return on investment on the machine is over 68 to 90-fold. Now, given that the machine had cost $1 billion, over $1 billion to build, that means over $100 billion in terms of economic impact. Now, of course, some people may contest this, so don't complain to us, complain to Hyperion. But even if the numbers were, if you consider this to be a little bit exaggerated, but still, nonetheless, the impact of a machine like this has really brought about societal, not only benefits, but societal changes. Like in the days of COVID, we estimate that the results from Fugaku to mitigate COVID allow people to have more societal freedom in Japan, which resulted in a downturn, saving the downturn rate of the overall GDP by about in the order of somewhere around over $10 billion. So these numbers are not, they're not too far off in terms of the benefits that these kinds of technologies bring. And this is now enhanced with AI. Okay. So with AI, they anticipate that our next machine will bring out more than 100x return on investment. Okay, so we're there, but what are we doing now? So of course we operate the machine, and but also we are a research lab at the same time. So we have embarked on several big projects. One is, of course, to pursue traditional HPC as that we advance our capabilities. And we always like to term this as something science of something versus science by. Science of is computing or AI or whatever as the target of scientific investigation, whereas science by is using these as tools to advance other sciences like biology or medicine or astronomy or climate and so forth. So we're doing both, but in terms of science of high performance computing, we're aiming, like towards zettascale computing, the next milestone, and do this with nominal power. We're not going to be like using gigawatts, but much more sustainable power budget. Of course, we are investigating what we can do if we are given such a capability. So we've been doing our feasibility study of the future machines, along with many of our partners, not just Japanese vendors, but a lot of the U.S. vendors, the usual suspects that you may know, the green ones, the red ones, and the blue ones, and so forth. And so this went on. This feasibility study went on for 3 years, from 2022 to 24. We have commenced. We have chosen our R&D partners, and the development has commenced. And hopefully, we'll have the next machine in operation and deployment in 2029, operations by 2030. And what we aim to achieve, what can be considered like zettascale or next milestone in like orders of magnitude increase in application performance at nominal and within the nominal power limit. And then there's AI, science of high performance AI, and science by high performance AI, way for science. And we have within RIKEN, not just our center, but we have 13 scientific centers at RIKEN. And the multiple centers are collaborating. A lot of the application centers on biology, material science, and so forth, to push forward innovations in science. How do we innovate science? The way we do science using advanced AI. So this is AI for science, and the project has started last year, and this is collaborating closely with Fugaku-Next project. But there are lots of new scientific, new breed of sciences that are being enabled by extremely high-end AI. And of course, there's also quantum. And at RIKEN, there are two primary efforts. One is a quantum who are actually building quantum computers or quantum gates, and or doing a lot of materials and more of a physics investigation of quantum computers, but they actually have built their own machines too. That's RIKEN Quantum Center. So, but their expertise is to build machines, whereas we're working on our role in working with Quantum Center and other quantum vendors like IBM and Quantinuum and others, is to push forward science by, or the infrastructure required to pursue this science by quantum, to pursue quantum algorithms or hybrid algorithms, because a lot of the algorithms that are in principle are hybrid, irrespective of being quantum allowed. And when you have any sort of complex algorithm that have both exponentially speed parts that can enable exponential speed up, but if there are portions that the quantum computers cannot achieve exponential, then it's pretty worthless to use quantum computers. Well, it's wasteful at least. So naturally, the most complicated problems render themselves to the hybrid computing. So we use the exponential part we leave the exponential part to quantum, non-exponential speed up part to classical. And so we are investigating this, the infrastructure, how we merge these machines, how we combine these machines, how we schedule the resources, how do we let people program. So all these issues, and what are the effective algorithms and applications. So we're working on all these issues, along with our partners, including RQC, but with other quantum vendors. And this is an ongoing project as well. Okay. Well, again, I don't have time to cover all the details of every project that we have. Just give you a sense of what we're doing. In fact, in terms of the use of AI in science, especially people who are already computationally savvy, that is people who are already using computational methods. then the use of AI in the loop and in the overall workflow has become quite a bit of a norm. So we have multiple, many examples where AI is being used. In fact, AI is penetrating various parts of the scientific process. So we have, I just listed 4 here, but but again, you can think of any of the Fugaku users. It's very likely that the team is already using AI as part of their portfolio, and it's pretty obvious because these people are computationally savvy. So having AI running on big machines is it can easily become part of their arsenal of tools. So we have people running surrogates. So in fact, combining with classical computing and traditional simulation to achieve dramatic speed up, essentially to achieve multi-exascale performance thing. For example, with ultra high resolution earthquake simulation, this is using all 160,000 nodes on Fugaku to run the earthquake simulation, but with the help of AI. I won't go into details, but allows you to do acceleration by various very clever preconditioners and also time step advances to allow 25 times speed up over just using classical methods. But you still get the same results. So this is work being done by the Earthquake Center at University of Tokyo. We have people, Material Science, this is one of our PIs. So he's using generative AI to generate various substances, in this case, photovoltaic cells or perovskite photovoltaic cells. So you would use AI to come up with candidate structures, and then you use classical material science simulation to filter out and also to measure the real energy values and so forth. And then you would send this over to companies, and they will actually synthesize and do the real tests. And this has allowed identification of new types of perovskite cells, which are lead-free, because one of the problems with perovskite cells is it contains lead and thus toxic. So the search is on to discover lead-free substances that have high conversion rates. And they've been able to come up with something like 25% conversion, which is really good for a solar cell. You can manufacturing teams have been using AI to generate various automotive shapes, and then using various parameters, not only to come up with aerodynamically efficient ones, but that are stable in terms of maneuver, but also aesthetically looking good. And then they will run through simulations to verify its properties and so forth, and to go through all the optimizations to come up with the best automotive design, where they can come with like 5,000 different good-looking designs that are also fuel efficient, whereas a human designer would take a whole career to generate 5,000 automotive designs. And the right-hand side this is a pharmaceutical. It's a common pipeline. It's a combination of multitudes of both classical simulations like molecular dynamics and AI synthesis. For example, we extensive use of various AI-driven synthesis methods, including something that was invented at DeepMind and so forth. So it's become quite the norm. In fact, we're advancing even more towards even the inferences requiring requiring significant, or any of the more traditional AI tasks requiring significant computational load. For example, this is work being done by Mohammed Waheed, one of our young, bright, upcoming rising stars in AI for science. So their task is they have this ultra high resolution images. In this case, like a picture or an image, X-ray image, ultra high resolution X-ray image of human tissue. And you're supposed to be, so you're a radiologist, you're supposed to identify whether there are cancer cells and so forth. But these resolutions are not your internet images, which are like, 4K or 8K. This is an image like 100,000 by 100,000. So ultra high resolution, or in some cases, as we'll see later, it could be 3D. So each image can be like a terabyte in size. Now, so you try to run an AI or have some sort convolutional networks, or in modern times you try to run like visual transformers. But let's say you're trying to run visual transformers, that's a big problem because the input context you're trying to fit. Even if you try to quantize and try to fit the images into the input context, this is a gigabyte image. This is a multi-gigabyte image, and if you have, let's say, you have Gemini, then your input context is only a million tokens long. So it's minuscule compared to the requirement. So how do you make it fit? So how do you handle a gigatoken size input context in a visual transfer? So so the team used classical HPC technique to try to fit this. So it's on the left-hand side. They use spatial hierarchical spatial decomposition, like octree or quadtree octree decomposition, and then you use space filling curves. So those who will be familiar with these HPC techniques, they say, this is what you ought to do. But of course, they actually did it, which reduces the complexity of the data structures from n squared to log n, so that's much more manageable. And then you apply some of these long context handling techniques, and to be able to barely be able to handle these types of humongous images that typically appear in scientific workloads, like in medical images, or sometimes in climate, images of climate, or in some cases images of your brain. So so we worked with various collaborators, Oak Ridge, Duke University, and so forth. And what we're doing is to apply the technique to dissect, basically to dissect a 3D image of a brain scan at 5 microns, 5 micron tactography. And the reason we want to do this is at this resolution, this allows you to reconstruct the neurons and all the connectomes, and how the synaptic connection between the neurons, thus giving you essentially the map of the brain structure. Now, but of course, you need to be able to take a 3D image from MRI or similar techniques and do 3D reconstruction, then segmentation. Again, these are being done on 10,000 by 10,000 by 10,000 image. So it requires some of the techniques that we have invented. Some of the reconstruction techniques we have invented, some of the segmentation techniques we invented, and so forth, that can deal with these kinds of ultra high resolution images at 3D. Now, once we have the reconstruction, then we can try to run it, because on a simulator, which is so we do also have a brain. We also have a brain science center at RIKEN. And along with our collaborators, we have been able to create a full human brain simulator. So the hope is, in the future, we'll be able to scan your brain and reconstruct this structure, and then run the simulation, which is effectively brain uploading you see in science fiction, allowing us to maybe live forever, like the recent programs like Alien Earth. So it's a little bit science fiction-y. Right now, we're not there yet with human brains. I'm sorry. We're starting with mouse brain. Let's complicate mouse brain and so forth. But all of these are on display at Expo 2025, which is being held in Osaka. So some of these are really some of these are quite intriguing to combine all these AI methods, being able to combine these AI methods and simulation to be able to do this cutting edge sciences that you think were science fiction. It can be also realistic too. So what we want to do is to handle infrastructure deterioration, meaning like roads and bridges, which is a huge problem and multi-billion-dollar industry trying to maintain and replace them and to repair them. So we have this RIKEN, we have this light source, which is very much like in the US, this will be like APS. In fact, or Spring 8, they collaborate heavily with APS. In fact, the next generation APS will have the same detector as Spring 8 because because Spring 8 is being upgraded, APS is being upgraded, and they're going to use the same detector developed at RIKEN. And so this is like if you think that some of the data centers are big, this is a very, very large structure. So the ring is about 1 kilometer in size. And then you have another extension, which is a linear accelerator, which is another kilometer in length. So, some of these instruments are huge. This is up in the mountains, about 70 kilometers away from me, from our center. But so we get but essentially this is a huge microscope. So what we do is take core samples and then try to do, again, 3D reconstruction, segmentation, and all that, lots of AI processing and also various simulations to allow us to have a method where we can be able, we can by taking the core sample to allow us to do a very accurate prediction of the structural deterioration with not just by looking at the surface, but really looking at the core, and then telling us whether we should be repairing or we should just leave it alone for a while, or some surface treatment and stuff, and all that stuff. But for the first time, these experts in concrete and infrastructure are really being able to tell what's really going on. So before they could only look at these horizontal images, sectional images, but now they can get a complete reconstruction of the 3D reconstruction and segmentation of what's inside, what are inside these, what's happening inside these concrete. Okay, so they say for science, there are more to come. How do we get to do things like hypothesis generation using LLMs, and how do we, how to code our experiments, or how do we do the coding? I'll cover that later, etc. But there are a whole bunch of things we can do also with things like foundation models or multimodal foundation models. But I'll get to that later. With respect to quantum. We have we're building this hybrid facility where we have multiple quantum computers and also hooked up to Fugaku and other medium-sized supercomputers. These are mostly GPU machines that we're putting together. And these multiple quantum computers some are built by RIKEN, some are IBM, some are Quantinuum, some are simulators that are run on GPU machines or on a Fugaku itself. And but our aim is to create this holistic infrastructure where we would be able to have people get on board, be able to program, then we can schedule these quantum jobs to really see and really to serve as a testbed, because HPC has been really successful by not just being theoretical, but having real infrastructure where people were able to use and experiment. Same thing with quantum hybrid. What are lacking, but what many of the centers and the world are trying to do is to try to build up the infrastructure so that people developing these applications and can come in and work on real problems. Because unless you work on real problems, you're not going to be tangible. So we have right now we have this IBM System 2, which just got commissioned this June. It's 156 cubic transmon superconducting qubits. We also have the Quantinuum H12, which is 20 qubits. This is an ion trap machine. We are negotiating with Quantinuum to increase it to 56 qubits. RIKEN's R-CCS. This is a collaboration with Fujitsu. There's another superconducting qubit. It's a 64 qubits, although Fujitsu announced that they have intention of going to much higher number of like more than 1,000 qubits in a few years. And they're also working with us to construct their own quantum center in their own premise. So we have a variety. We're getting, and also we're collaborating with other centers that are deploying other types of qubits like neutron atoms and so forth. So we have quite a bit of a comprehensive sets of quantum machines at our disposal. But our real work is not is to assemble these machines, but also to build this whole software stack and ecosystem, including common software stack, programming, scheduling, resource scheduling, communications, et cetera, and also simulators, because we do need quantum simulators too, because still these quantum computers are still NISQ machines. So we need simulators in order to see what would happen when we have exact behavior on our machines. And so it's a continuing project, and here are some of the machines. These are already there for real, and we're developing our scheduler and also like workflow, Quantum-HPC workflow scheduler, and so forth. But we have some early results. So this joint work by IBM and RIKEN, our application team, where we were able to basically use, at this point, when we published the paper, they use 77 qubits on the IBM system 2 and 6,400 nodes on Fugaku. On the Fugaku, so this was basically doing sampling, using quantum computers to sample in space. And we take a lot of the samples and then find the optimal by running a very large eigenvalue problem, solving a very large eigenvalue problem involving 6,400 nodes. More recently, this has been expanded to use about half of Fugaku, about 80,000 nodes. So it's a very large eigenvalue problem. The similar algorithms are being done by people like Quantinuum. So where instead of using eigenvalue solver, they're using quantum sampling, and then they're using samples at training sets to train a materials AI, so that they can sample in space where traditional simulation will not be able to generate these samples, and thus giving much higher fidelity to the surrogates and so forth. So, but it's a very similar scheme, and I think these will become more popular as days go by. So this is, but they have been able to achieve what could be considered a quantum, not so much quantum advantage, because there could be other algorithms to solve the same problem in Fugaku. If you use the same algorithm, actually, this is much faster using quantum and hybrid. But being able to solve some of the problems, including for these real molecules like ferric sulfuric substance. And so this is something we consider as being demonstrating that quantum computers are useful. And we are now we have solicitations of multiple companies, including like Mitsubishi, like Sumitomo Chemical, SoftBank, Toyota, etc. Some of the major companies are signing up because they have quantum teams that are investigating, but they want to use the infrastructure and work with us to come up with problems, try to solve some of the sample problems they have. And when we have in maybe like 5-10 years, when we have real machines that are at DQC and have a much higher number of qubits, and we have zettascale machines on the classical side, we hope to be able to demonstrate quantum advantage over many classes of problems. Yeah. Okay, so that's a quantum. Okay, what about classical computer? Well, if you look at the history of evolution of national lab and vendor relation for the Japanese supercomputers, which have had its accolades being like #1 on rankings, But but if you look very carefully, a lot of these results have been achieved mainly by very, very diligent development activities by the vendors, and not so much the national labs. For national labs, do the problems, work on the algorithm problems, but the machines and the systems and so forth have been mostly developed by the Japanese vendors. For example, if you take a look at the Earth simulator back in 2002, over 20 years ago. So it was number one, but it was achieved with NEC's aging SX design, was a vector parallel machine. But for the machine of that type, it was unprecedented in size. But basically, it was NEC's design. So the hosting institution really didn't have much to say. But it was NEC who had an army of engineers to create this machine. Very similar with the K computer, RIKEN for the first time was granted this national center status. But most of the R&D was done by Fujitsu. Now, Fugaku, our current machine, RIKEN got more involved. And so part of the Fugaku's design activity was done by RIKEN, but was still very much dominated by our contracting vendor, Fujitsu. So our next machine, Fugaku-Next, we intend this to be much more a trilateral development effort, not just by us, but the two partner vendors. But we will be very proactive, because now we have a center with a few hundred people, and also we have various partners that allows us to work much more extensively on the design of the machine, and also the software and algorithms, and how we operate the machine. And the vendors can focus more or less on the hardware, but still work with the vendors extensively to help them to design the hardware. So during the 3 years we had undertaken the feasibility study. Unlike the last time, when it was predominantly Japanese vendors, from the onset, we solicited multiple U.S. vendors, or the usual suspects, and to participate. And we were very honored that they participated. So we had not just Fujitsu, but had like NVIDIA, AMD, Intel, HPE. I don't know how you might consider ARM. ARM could be a UK company, could be a US company, could be a Japanese company. But either way, these are ARM would be a non-traditional Japanese company. It's owned by a Japanese person, but so we worked for 3 years, and the conclusion was that if we extrapolate our hardware advances from what we had in 24 all the way up to 29, looking at the semiconductor advances, the various advances that the vendors were foreseeing especially in terms of acceleration and so forth, we can come up with a machine where the HPC capability would be about 5 to 10 times effective increase, which is not a lot, because from K to Fugaku achieved about 30 to 40x. But because of Moore's law is slowing down, unfortunately, the expected speed up increase in performance was less than order magnitude. AI performance would increase significantly. We would be able to, the projection across most vendors with reduced precision and such, we can achieve somewhere close to a zettaflop, even within the 40 megawatt power limit. But then we said, okay, we looked at these numbers, and the numbers differ. Different vendors had different strawman proposals, and we worked very tightly with those kind of vendors. And they came up with these strawman proposals, which we refined working with them. But in the end, they ended up being somewhat largely similar. And that, of course, that's obvious because people working with the same silicon and same technology, like the same HBM roadmap. But then we said, can we do better? So we're a research institution. We want to do better than what the vendors propose, because otherwise we wouldn't have our rationale of being an advanced research lab. So we signed a deal with DOE, and we first evaluated all the vendor proposals and came up with two partners that we decided to work with. In fact, this was a very close competition, but in the end, Fujitsu and NVIDIA won our partnership call. There was a big solicitation and bidding and so forth. So a lot of vendors participated, and in the end, the development contract working with us was awarded to these two companies. Fujitsu principally working on the CPU and the other parts system, NVIDIA working on principally the GPU and other parts system. But of course, we work mostly on software and applications and such. But of course, we'll help these companies design their next generation machines, the CPUs and GPUs. So we receive a lot of attention. For those of you who know the top brass at NVIDIA, you can tell that the guy who's in the photo holding hand on the right hand side is Ian Buck, and the guy on the left hand side is a guy named Vijay Mahajan, who's the CTO of Fujitsu. And you see a little bit of me in the background, a little fuzzy. But of course, we made headlines at Nikkei newspaper and all that, so we received a lot of attention. So, so we're right in the midst of this preliminary design phase in 25, and we hope to do detailed design and deployment in 29. At the same time, we'll be conducting another feasibility study, so that we'll be in 5-year cadence in developing machines. Now, you might argue this: can we shorten this? Well, maybe so, but this is more of our long-term cadence, and we may, Fujitsu for Fujitsu and NVIDIA, of course, they'll be producing chips at 2-year cadences, but based on the results of some of the investigation we'll do with them collectively. And you have a lot of organizations that will work with us, the RIKEN and GPU CPU vendors, namely Fujitsu and NVIDIA, but also there are other contractors. There are others, computing centers. We have DOE labs who are in close collaboration. In fact, we have a big meeting next week. Of course, our user community, and we have a high performance software foundation. We'll do a lot of software open source and such. Okay, so what's the objective? Well, so like I said, Fujitsu will develop the CPUs, and what we have in mind is with them is a CPU called Monica X, which will be probably the best. We hope will be the best CPU of the time, and not a CPU not just being a subordinate to a GPU, but it can stand its own with respect to, for example, AI performance. So it's not as good as GPU, but it will probably have the highest AI performance for a server CPU of any server CPU, more than things like Xeon Max and so forth. So maybe Google could be interested in deploying these in the cloud. And of course, NVIDIA will do its thing with them, but we will work with them to try to help them to at least have a SKU that's appropriate for HPC AI purposes. But of course, we'll do a lot of other work which I can't disclose right now. And we also need to modernize Japanese applications, which have been predominantly CPU-based, to upgrade these to GPUs and other accelerator-based code base. And of course, we'll be utilizing significant AI assists like AI codings and so forth. But it's one thing to do AI coding with your standard, Python or more internet-friendly types of codes. But we need to modernize Fortran codes as such. So do these AI coding coding agents. They work very well with arcane Fortran code. Can we use them to modernize? Well, that'll be one of the big technical challenges. And of course, we want to establish long-term. There are lots of other technologies that we cannot deploy in 29, but we know either exist or it's in the back burners in research. It's our long-term commitment to try to, have a sustainable research so that we will, for that, in the various cadences we have, we'll be ready when these technologies are mature enough to be deployed in mass. Things like very advanced photonics, very advanced memory technologies, VD memory technologies, of course, quantum and as such. Now, of course, the goal is to build a machine, but that's probably a secondary because we know the machine will be built. The question is whether it'll be like the real top tier machine that people will want to replicate. Like I said, we are one of the big things we need to do is to have established a basis for to allow users to come in with their arcane, let's say their arcane Fortran codes, and be able to modernize the code in various ways. Of course, there's no single pathway, and but we are experimenting with various coding agents. Also developing various more theoretically sound ways of doing program transformation for these AI agents to do, so that transformations they may do will be correct, semantically correct. And of course, we're building a testbed, a modest 2000 GPU testbed, which will serve as a production AI for science or Quantum-HPC cluster. But also serve as a development prototype for 2 generations past development prototype for Fugaku-Next. So it's a modest machine, about 2,000 plus Grace Blackwells. So it's not a huge machine, but it'll be very useful. So we have these phase deployment plans: phase 1, phase 2, phase 3, going phase 4. We have a real Fugaku-Next. And there are a lot of details about how we develop software. We already have a software stack for Fugaku that's been virtualized. This is a collaboration with Amazon, with AWS, and hopefully this can be done on GCP as well. That we now
I'll talk about that.
we can replicate the environment.
Satoshi, we only have a few minutes left, and I've got a few final comments to make about our upcoming programming. So we're going to probably have to cut off Q&A today, but if you can summarize, I will then jump to some stuff. And then I want to bring you back because I see you have lots of other stuff. So I'd like to do a part 2 of this as well, because I see some slides like this that really deserve their own session, and how we're going to do lower performance computation from AI processors, but make it work for scientific computing. I see you've got some things like that in here. So why don't we schedule a part 2 with that?
Okay, yeah. So I'm sorry, I didn't.
No, it's great. This is all great. This is exactly what I wanted, because it's always for Google Cloud and our desire to be the best cloud for science. You want to make sure that you're tracking what the world's leading laboratories and centers are deploying on-prem. And I actually will be talking in about 3 weeks on Google Cloud for Science, and there's going to be some overlap with what some of I talk about, what I present, with the directions you're headed here. So not entirely, but some. And I want to make sure. So this is a great stage setter for that presentation in 2 weeks.
Okay. So just a preview of. I'm sorry for running over time. Preview of part 2. Just as Jay said, we're considering how, given the direction of AI hardware, and of course there are lots of discussion there too, because on one hand, for example, NVIDIA just announced their disaggregation SKU for the Rubin GPU, you may know, which is heavily geared towards computation and not so much on bandwidth, and that may make sense, right? Because for the current moment, because right now, if you look at the inference workloads, the prefill versus the prefill, then you have the decode. The prefill is right now still very computationally intensive, and that's why they want to do the disaggregation. That said, is that going to persist? And that's there's a big debate. Because there are a lot of sparsity. Well, essentially, what can be classified as sparsity that are being exploited, which, from an information theoretical point of view, you can see that a lot of these models are way too big for the information they contain. Right? I mean, at least the dense models. That's why sparsity works. Anything from MOE to like sparse attention to anything like that. The reason they work is because the models right now overkill. So are the hardware geared towards that? Are they going to persist, or will people find ways to be much more clever and the hardware will follow? But on the other hand, we have HPC workloads, and the HPC workloads also need to adapt to how these AI hardware is. So it's a sort of a very complicated landscape where you have all these evolutions of AI and their models, and you have HPC and the evolution algorithm, you have the hardware development, and these are very, very complicated in terms of the relationship.
Satoshi, I'm going to have you save that for the part 2 because that is so complicated.